Hi, welcome to this lesson on covalent bonding, specification reference 3.1.3. And in this lesson we want to do three things. We want to be able to describe a covalent bond, and we want to describe a coordinate bond, which is a type of a covalent bond. And we also then want to have a look at the properties of covalently bonded molecules, whether they be simple molecules or macromolecules. That's all we have to do. And firstly, let's remind ourselves that molecules, that's simple molecules, they form when two or more atoms bond together. And the atoms are generally non-metal atoms. So when a non-metal atom and another non-metal atom share electrons and make a covalent bond, that would be a molecule, a simple molecule. And examples of course would be carbon dioxide. All right, so you can see that molecules can have double covalent bonds. It can be water. Water is another example of a simple molecule. And I'm just going to draw in the lone pairs here as well. We'll come to that. Draw lone pairs like that. And the straight lines represent the covalent bonds between the two hydrogen atoms and the oxygen atom in the middle. The atoms don't have to be different, they can be the same. So a chlorine atom will bond covalently together with another chlorine atom, and that will make a Cl2 molecule that you'll be familiar with from GCSE. And of course molecules can also be slightly bigger than this, in fact a lot bigger in some cases. So for example ethanol, C2H5OH, ethanol is a molecule, and I'll just draw that out for you quickly. We've got two carbons, and this carbon would be surrounded by three hydrogens. This carbon would be surrounded by another couple of hydrogens, and we would have the OH alcohol group on the end there, each of those straight lines being a covalent bond. And because all of these molecules are discrete, all right, they're all discrete, they're not bonded to anything else, they're just bonded to themselves. That's why we call them simple molecules as opposed to macromolecules. Yes, and so in covalent bonds, as we know, two atoms share electrons, and they do that so that they can both have full outer shells. So let's review what we know already from GCSE with the example of, say, fluorine. So if we've got a fluorine atom, the outer shell we could draw as a circle, and then we could draw in how many electrons? Group 7 electrons for one fluorine atom, and we could that's going to bond with another fluorine atom, and in its outer shell it's going to have 7 electrons, of course, also, 6 of which are paired up and 1 of which is on its own. So the covalent bond happens between the unpaired electrons. So covalent bonds happen between the unpaired electrons, and so we'll draw that together like this. All the paired up electrons are unaffected, but our other fluorine atom shares its unpaired electron with the other fluorine atom, and we get a diagram that we draw like that. And then the electrostatic force exists here between the positive nucleus and this area here of high electron density with the two bonding electrons, which of course is negative. So those opposite charges attract, that is the positive charge of one nucleus and the negative charge on the electrons, and the same happens on the other side. So we've got two little electrostatic attractions there that form the covalent bond in combination. So that is the combination, that is the force that holds the two fluorine atoms together. And that's the covalent bond that is sometimes drawn as just a single line. What we're going to do is we're just going to write out the electron configurations of these fluorine atoms. So this fluorine atom, let's call it fluorine 1, is going to be 1s2, 2s2, and then it's 3p5, like that. And we could draw the orbitals as well, so slightly higher for the second orbitals. Okay, so in here we've got all squished up, we've got a pair of electrons, up and down arrows, and I should have drawn these boxes bigger. So that's how you can see the electron configurations. And if we draw it for the other fluorine atom, and I'm just going to draw it as a mirror image, a reason why you'll see in a minute, I hope. So that's also going to be 1s2 and 2s2 and 3p5, of course, and that's going to have its orbitals arranged similarly. And what I'm going to do is I'm just going to draw this overlapping like that. So the 1s2 orbitals are full, the 2s2 orbitals are full, and two of the p orbitals are full as well. And they're all full, and the unpaired electron, this electron here, is going to go in the orbital that is now shared. Okay, and so that becomes the bonding pair and is the covalent bond. So the takeout from this is that covalent bond occurs between unpaired electrons of the constituent atoms. And our next point is this. It is that atoms can promote electrons into unoccupied orbitals in the same energy level to form more covalent bonds. To illustrate this point, I'm guessing this doesn't make sense straight away. So to illustrate this point, let's have a look at methane. And we'll be familiar with methane from GCSE, and you know that methane is CH4. So we'll look at methane CH4, and from GCSE you know that the carbon atom is in group 4, it has 4 electrons in its outer shell. So just drawing the outer shell, yeah, we'll draw 1, 2, 3, 4 electrons, and we know that it likes to have 8 electrons, and then the hydrogens are going to come along and provide the other 4 electrons. So there's going to be a hydrogen here with a bonding electron there. Hydrogen here shares its electron, and another hydrogen shares its electron, and likewise for the 4th hydrogen atom. And so you can see that we're going to get 4 covalent bonds like that, like you're familiar with, and that's all fine. But earlier on, didn't we say that covalent bonds happen between unpaired electrons of both atoms? And let's just check carbon. Let's just check the electronic structure of carbon. So carbon has 6 electrons, doesn't it? So we're going to have 1s2, 2s2, and then 2p2. If we draw the orbitals, it's going to be 1 orbital there, which will be occupied. It's going to have another 2s orbital, which is fully occupied, and the 2 orbitals, well, there's 3 orbitals rather, in the p subshell, and we've got a first unpaired electron and then another unpaired electron. So you'll remember from the London bus rule that these electrons these two 2p electrons don't pair up, they go into unoccupied orbitals. So you can see from the electronic structure there that carbon only has 2 unpaired electrons. So how can it form 4 bonds? Well, it does so by a process called hybridization, which is the full process of hybridization is not covered in the A-level spec, all right? But it's interesting for your understanding to understand this. So what happens with carbon is that it promotes, as the title of the slide suggests, it promotes some of these electrons, and I'll show you how. So the 1s electrons, okay, they're in a different energy level altogether, so they're not promoted. But what happens is one of those 2s electrons is promoted up to, right, so there's our 2p electrons that were already there, and this is the 2s electron that's been promoted up to the 2p orbital, the empty 2p orbital, because it's in the same energy level, right? 2s and 2p are all in the same energy level, right? So you can promote one of those 2s electrons up to the empty 2p orbital, such that now you can see you've got 4 unpaired electrons. And so if we write the hydrogen electrons in red, right, one of them's going to go in here, one of them's going to go in here, one of them's going to go in here, one of them's going here. So that's the 4 hydrogen electrons that are contributed by the 4 hydrogen atoms, and that's how you get your 4 hydrogen bonds, the 4 covalent bonds between 1 carbon and 4 hydrogen atoms. So moving on, we also know that there are also double and triple covalent bonds, and an example of a double bond. Example of a double covalent bond is in carbon dioxide. So let's just draw out our dot and cross diagram for carbon dioxide. So we've got a carbon atom in the middle, and we've got an outer shell of carbon electrodes, and it's done its hybridization promotion thing. So it's now got 4 bonding electrons. So we're going to draw. Let's draw one of them over here. Let's do the carbon atoms as dots. So it's got one there and one there and one there and one there, because what it wants to do is it wants to join up with oxygen, and oxygen's outer shell will draw like this, not really asymmetrical like that, and oxygen's atoms electrons will draw as crosses. Right, so it's got 2 unoccupied electrons, but it's also got 6 in its outer shell. You know that's oxygen group 6 electrons in the outer shell, and the other 4 electrons are in pairs, and they're called lone pairs. So these are called lone pairs of electrons, and it's 2 unpaired electrons join with the 2 of the unpaired carbon electrons, and the other oxygen atom is going to look like this, right, with its 2 unpaired electrons joining in those covalent bonds, and again it's got 2 lone pairs on the other side there. And so you can see in this bond here, let me switch to blue. We've got 1 covalent bond here, and in that covalent bond there are 4. In that bond there are 2 electrons, but there's another covalent bond there between the other 2, and the same on this side. There's 2 pairs of bonding electrons represented by two straight lines like that. So you could also draw your carbon dioxide molecule just like that. Yeah, so that's an example of a double bond. Let's do an example of a triple bond. And the ubiquitous triple bond is between nitrogen atoms in an N2 molecule. And nitrogen does a bit of promotion as well. So nitrogen, it's going to be 1s2, 2s2, 2p3. And if we draw the orbitals, we're going to have those two 1s electrons like that, and then at a higher energy level we're going to have our 2s electrons, and we're going to have 3 orbitals for our p orbitals, and of course they are all going to be unpaired because they occupy new orbitals before they pair up. And so as you see, contrary to what I said earlier on, as you can see you've got 3 unpaired electrons there, and they're the 3 electrons that are going to join in these 3 covalent bonds. So we can draw that in the traditional way with the outer shell of one nitrogen atom, and that you could draw overlapping with the outer shell of another nitrogen atom, and so you're going to have those 3 unpaired electrons there from the left-hand nitrogen atom, as well as this lone pair here, and you're going to have the same on the other side. Let's draw them as dots, and you're going to have 3 dots in there as well. So we can represent those 3 pairs of electrons with 3 lines like that, or indeed we could draw it as in a displayed molecule like that, and that would be our triple bond. And as you can see, the nitrogen atoms are both like this. They get a shared electron from the other nitrogen atom, so that they now have a full outer shell and quite stable electronically. Okay, so just reiterating again about simple covalent molecules, we can say that compounds that are made up of lots of individual molecules, they are simple covalent compounds, like a chlorine molecule, for example. And the reason that I mentioned this now is just to clarify that a chlorine molecule has a strong covalent bond between the 2 chlorine atoms within the molecule, and it's a gas, all right, so at room temperature. So you know that a gas has a low boiling point, all right. So why is that? Well, the thing is about simple covalent molecules is when they boil, the bond that is broken is not the covalent bond within the molecule. It is the intermolecular force between the molecules. So this is the intermolecular force, not even called a bond because it's so weak. It's an intermolecular force between the molecules, hence inter, and that's weak, and that leads to low boiling points. And what's more, there's no charge on these molecules and no delocalized electrons, so they are also simple covalent compounds are also good insulators or poor conductors. So moving on to a different type of covalent structure, we're going to look now at giant covalent structures. And giant covalent structures, such as I'm underlined in here, also known as macromolecules. Macromolecules. molecules. So macro because they have a huge network of covalently bonded atoms. So here we're looking at graphite. And this is a tiny part of a bit of graphite. And you can see the layers there. Layers are supposed to come out of the page and go into the page. There's layers of hexagons. And here we can see carbon as diamond. So graphite and diamond are two allotropes of carbon. And they're the two that you need to be familiar with when we're talking about giant covalent crystals. And carbon is special because it can form 4 very strong covalent bonds and make structures such as these. And they're both very interesting. So we're going to have a look at each one in a little bit more detail. Yeah, so with graphite, the carbon atoms are arranged in sheets or layers of flat hexagons. You can see the hexagons here, and these interlocking hexagons are supposed to be horizontal, coming in and out of the page, and they go on and on and on and on with billions of atoms. And so here we've got 2 layers of these layers of hexagons, and what you can see is that in graphite, if you take this carbon atom here, you can see it's making 1, 2, 3 covalent bonds with other carbon atoms around it, as are they all. And as you know, carbon has 4 outer electrons, and so there must be a spare electron somewhere. And that spare electron, that 4th electron, that 4th valence electron, exists between the layers. Right, so I'll just draw it in here for now. And each one of these carbon atoms, this one's got 3 covalent bonds as well, so another spare electron exists between the 2 layers. And so each one of those carbon atoms contributes this delocalized electron. And these delocalized electrons explain the conductivity of graphite. So graphite is a non-metal, as you know, but it still conducts electricity. Also, you'll know that. And it does that because of these delocalized electrons, these 4th outer electrons that are not involved in covalent bonds that exist between the layers. Because if you were to apply a potential difference across, let's say, across this sample of graphite, these electrons are free to move, and they could move and carry the electricity, or be the electricity. So that explains how this non-metal called graphite can conduct electricity. Also, what you might know about graphite is that it's used as a lubricant. Well, how come it's used as a lubricant? These bonds here that are illustrated between the layers are weak intermolecular forces. These are weak intermolecular forces. They're not covalent bonds. They're much weaker than covalent bonds, and they just exist because there are delocalized electrons in the middle, and if these carbon atoms have lost electrons, then they have a positive charge, and you can see there's going to be some sort of electrostatic attraction between the carbon atoms that have lost their delocalized electrons and the delocalized electrons themselves. But that's quite weak in the case of graphite, a bit stronger in the case of metals, but that's weak intermolecular forces. So you can see then that these layers might be strongly attached, the atoms will be strongly attached to the other atoms in the same layer, right? But each layer is only weakly bonded to the next layer. And so that means the layers can slip over each other. So the layers can slip over each other, which makes it feel slippery. And that's indeed how your pencil works. So you're basically smearing bits of graphite onto your piece of paper when you write with a pencil, as you scrape off layers of these hexagons of carbon atoms. And that allows them to be used as lubricants. If you ever need a solid lubricant, right? Most lubricants are liquids, of course, like engine oil, for example. But if you ever need a solid lubricant, chances are it will be graphite. Okay, another interesting feature of graphite is that these covalent bonds here, the length of those covalent bonds is actually quite short compared to the distance between the layers. And that makes it quite low density. All right, the fact that the layers are quite spaced out. So if it is low density, it's still actually quite strong because the covalent bonds are very strong. So it's a combination of low density and strong, which allows it to be used for sports equipment, for example, like tennis rackets, where if you want to swing your tennis racket really quickly, you want it to be light, but at the same time you want it to impact the tennis ball with strength, and so it still needs to be strong, and so graphite is a good material to make tennis rackets out of. As far as the melting point of graphite is concerned, it's quite high. Melting point of graphite, well, it doesn't even melt, it sublimes, and it sublimes at about 3,900 Kelvin, and that's because the bonds that are broken when it sublimes are the covalent bonds, right? And the covalent bonds are very strong. So the sublimation temperature there at 3,900 Kelvin, very high. And the last little feature of graphite that we want to be aware of is that it's insoluble, all right, in any solvent. It doesn't want to break down and form bonds with any solvent, and so that makes it insoluble. And now we're aware of that as well. So diamond is the other allotrope of carbon, and in diamond each carbon atom is bonded to 4 other carbon atoms. So if we take this carbon atom, for example, you can see it's bonded to 1, 2, 3, 4. You'll remember that graphite, the carbon atoms were just bonded to 3 other carbon atoms. So here in diamond you can see that all of the outer electrons are used in covalent bonds, and they make this tetrahedral shape here. All right, and that tetrahedral shape is a crystalline lattice. Okay, so one of the results of all 4 outer electrons being involved in 4 covalent bonds means that there's no delocalized electrons. So no delocalized electrons, as there was no delocalized electrons, right? So does not conduct electricity. As it happens, though, it does conduct heat quite nicely because it's so rigid. A diamond is so rigid that it transmits vibrations very effectively. So diamond does actually conduct heat quite well, but in a different manner to that which a metal would conduct heat. Now again, these covalent bonds are very strong, so the CBs are very strong, and that makes diamond very hard. It doesn't have any layers to slide over each other, so it's not slippery. All right, so that makes diamond very hard. And in which case, of course, it's used for diamond drill bits and saws, applications like that where hardness is a benefit. And lastly, in the same way as graphite, diamond is not soluble. For it to be soluble, these covalent bonds would need to be broken by the solvent, and they're too strong, so they don't dissolve, and the diamond will just stay as a diamond even if you left it for hundreds of years in a solvent like water or whatever. So we'll move on now to coordinate bonds. And coordinate bonds are those covalent bonds where one atom provides both of the bonding electrons, as opposed to two atoms sharing electrons. So one atom provides both of them instead. And we'll look at an example. The example is going to be ammonia. Ammonia, you'll remember, is NH3. And when that reacts with an acid particle, a hydrogen ion, you get a coordinate bond formed, and we'll see how that happens. So you'll remember that nitrogen is in group 5, so it's got 5 outer electrons, and it's going to bond with 3 hydrogens, and we'll draw them here like this, and you'll see why in a minute. And let me just draw hydrogen's shell. For our 3 hydrogens. Okay, so let's do the hydrogen electrons first, shall we? Should we put them, we'll make them blue dots. So there's 3 hydrogen electrons. As you know, each hydrogen atom only got 1 electron, and there we have it. Nitrogen, of course, is in group 5, 5 outer electrons. We'll draw those as, let's make them red crosses. Okay, so one of its outer electrons is going to be involved in the first covalent bond, normal covalent bond. One of its electrons involved in this bond, and one of its electrons involved in this bond. So that's 3 nitrogen outer electrons we've accounted for. Still got 2 left, and they are paired up in its own orbital, so we'll draw them there like that. So that's what the ammonia molecule looks like in a dot and cross diagram. But let's say we were to react that with a hydrogen ion. Now, you know the hydrogen ion is just a hydrogen atom that's lost its electron, but it only had 1 electron anyway, so it's just a proton swimming around. So its 1s shell is now empty. When it was an atom, it had 1 electron in it. It's lost that electron, so that 1s orbital is now empty. And so that empty 1s orbital of the hydrogen can accept the lone pair, the pair of red crosses there on the nitrogen atom of the ammonia molecule. And we would draw that like this. You'd have your nitrogen outer shell like that. And let's draw it just the same as it is up there. We still have our hydrogen atoms as they were. With their blue dot electrons. So nothing different as yet, but what we can say is this hydrogen proton looks just like the other hydrogen atoms, because it can't tell the difference between what was its old electron and the bonding pair. The covalent bond that is now a coordinate bond So this bond here with the two red crosses is now a coordinate bond. But of course we've still got that positive charge, this positive charge here that was with the hydrogen atom, and so this is now an ion, so we draw it in square brackets and put our plus at the top right hand corner. And just to be clear, so that there's no dispute, this pair of electrons here, this is our shared pair of electrons, but it's been donated by the nitrogen atom, and that forms the coordinate bond. And so this is the coordinate bond. Like that. And if we were drawing that in a displayed formula, this is how we would draw it. So you draw your N normal covalent bonds for your original three hydrogen atoms, but the coordinate bond is just differentiated from a normal covalent bond by an arrow like that, and the direction of the arrow indicates which atom has donated the pair of electrons. And so that's how you draw it as a displayed formula. Okay, so that concludes the lesson on covalent bonding, but lastly let's just make sure we've covered everything off. We described a covalent bond, and we even looked at orbitals and assessed that covalent bonds take place between unpaired electrons. And we also looked at coordinate bonds, where we saw that one of the atoms in the coordinate bond provides both of the bonding electrons, and we described that in a displayed formula using an arrow. And we also talked about a few of the properties like melting point and conductivity, for example, of covalently bonded molecules, whether they be simple or macro. And so we did all that, and hopefully that's been clear for you.